The driver presses the clutch pedal, reaches for the gear lever, and tries to move the automobile into another ratio. The engine is running normally. Nothing appears to be broken. Yet somewhere beneath the floorboards, metal suddenly chatters against metal. The lever resists. The driver eases it back, adjusts the throttle, tries again, and this time the gears slide together with barely a sound. To an experienced motorist of the early 20th century, the difference between those two attempts could lie in a fraction of a second and a feel for machinery that no instrument displayed. Changing gear was not simply a matter of selecting first, second, or third. The driver had to judge what was happening inside a box of rotating shafts and toothed wheels, then manipulate the clutch and engine until parts hidden from view were moving at compatible speeds. Get the timing right, and the gearbox seemed cooperative. Get it wrong, and the transmission announced the mistake in a harsh metallic grind. This was not necessarily evidence of damage or bad workmanship. It was a consequence of how many early gearboxes operated. The controls could tell the transmission which ratio the driver wanted, but they could not automatically prepare every rotating part for the moment of engagement. That difficulty had roots in the earliest years of automobile development, when engineers were still deciding what a motor car should look like and how its power should reach the road. Many first attempts resembled horse-drawn carriages fitted with engines, belts, chains, friction mechanisms, and several kinds of gearing appeared, while designers searched for a practical way to connect an internal combustion engine to wheels that had to operate across a wide range of road speeds. The engine itself created the need for multiple ratios. Starting from rest, climbing a hill, accelerating, and cruising did not place the same demands on the drivetrain. A low ratio allowed the engine to turn quickly while the car moved slowly, providing greater mechanical advantage. Higher ratios sacrificed some of that leverage in exchange for road speed. Multiple gears solved the problem in principle. Changing between them while the machinery was already rotating introduced another. In France, Panhard and Levassor helped establish an arrangement that would influence automobile architecture for decades. By 1891, the company had adopted what became known as the Système Panhard, the engine at the front, followed by a clutch and gearbox, with power ultimately reaching the rear wheels. It was a major step toward the layout later generations would regard as conventional. Early transmissions associated with this type of design often used sliding gears. Selecting another ratio could mean physically moving one gear until its teeth entered mesh with another. The mechanism gave the car practical choices of torque and speed, but the teeth being brought together did not necessarily arrive at the engagement point under compatible conditions. Imagine one toothed wheel turning rapidly while another approaches at a substantially different rate. The teeth do not simply fall into place because the lever has reached the correct position. Their faces strike, skip, or refuse to enter mesh, bring their speeds closer together, and engagement becomes far smoother. That simple relationship explains why an early gearbox could grind even when every component was fundamentally sound. The driver had chosen the correct ratio, but had not yet created the right conditions for the gears to accept it. The clutch helped by disconnecting the engine from the transmission, but pressing the pedal did not automatically place every shaft at the speed required for the next gear. The motorist, therefore, had to learn the rhythms of the machine. Engine note, road speed, the rate at which the car was slowing, and the feel of the lever all became clues. An experienced chauffeur might allow exactly the right pause before completing a shift. Another person in the same car could make the gearbox seem almost unmanageable. The transmission behaved less like a simple selector and more like a mechanism that demanded timing. Force rarely improved the situation. If the rotating parts were badly mismatched, pushing harder on the lever merely made their disagreement louder. This reputation later helped give unsynchronized transmissions the nickname crash boxes. The term can make them sound crude beyond usefulness, which would be misleading. Such gearboxes carried automobiles over difficult roads and remarkable distances. In capable hands, they could be shifted quietly and precisely. Their limitation was that smooth operation depended heavily on the person driving. Early motorists already faced enough work. Starting an engine could demand physical effort. Ignition timing might require manual adjustment. Throttle arrangements were not always standardized. Steering was heavy, brakes were primitive by later standards, tires punctured frequently, and road surfaces varied enormously. Gear changing added another learned procedure, and its mistakes were unusually public. A poor shift produced a sound everyone nearby could hear. Engagement might fail entirely, forcing the lever back into neutral while the vehicle continued losing speed. On level ground, that could be inconvenient. On a steep climb, a missed downshift could leave the driver trying to recover the correct ratio as momentum disappeared. The practical answer was not to fight the gears, it was to prepare them more carefully. Drivers developed the technique known as double clutching, or double declutching in British usage. The sequence sounds elaborate because it turned a hidden transmission requirement into a series of deliberate human actions. The driver disengaged the clutch and moved the gearbox into neutral. Instead of going immediately into the next ratio, the clutch was released again while the transmission remained in neutral. This reconnected the engine to part of the gearbox, allowing the throttle to influence its rotational speed. The clutch was then depressed a second time and the next gear selected. On a downshift, a well-judged burst of throttle could raise the relevant shaft speed toward that required by the lower ratio. If the timing was close enough, the gear entered with little protest. Double clutching, therefore, was not an eccentric ritual left over from primitive motoring. It was a practical solution to a specific mechanical condition. The driver's actions created the speed relationship that the transmission itself did not yet establish automatically. The technique also explains why proficiency mattered so much. A chauffeur familiar with one car could learn how quickly its engine lost revolutions, how much throttle a downshift required, and how long to pause before another engagement. The same procedure performed mechanically, without sensitivity to road speed or engine behavior, was less successful. Shifting became a form of accumulated experience. That arrangement remained acceptable while automobiles were comparatively specialized machines. Wealthy owners could employ chauffeurs. Enthusiasts took pride in mechanical knowledge. Commercial drivers learned their vehicles as part of their profession. But the automobile industry was moving toward a different future. Production increased, manufacturers sought customers with little technical background, and cars were gradually expected to behave like consumer products rather than equipment that demanded apprenticeship. Other aspects of motoring were already changing in that direction. Electric starters reduced dependence on hand cranking. Controls became more standardized. Bodies grew more comfortable and enclosed. Engines improved in smoothness and reliability. A transmission that required precise timing from the driver began to look increasingly out of place in a car otherwise designed for refinement. The problem was no longer proving that a skilled person could shift without grinding. The industry had ample evidence of that. The harder question was whether the mechanism could be made more tolerant of ordinary human operation. Earl A. Thompson approached that question with unusual persistence. Born in Oregon in 1891, Thompson became interested in transmission mechanisms during a period when the American automobile industry was expanding rapidly, but conventional gear changing still relied heavily on established sliding gear practice. In March 1918, he filed a patent application for an automatic gear shifting mechanism. The patent, granted in November 1922, described a system more elaborate than the compact synchronizer, later associated with passenger car manual transmissions. It dealt with gear selection and shifting as well as synchronization. Yet within that broader mechanism was an idea of lasting importance. Before two transmission members were allowed to engage, their velocities should first be brought into coordination so that the shift could occur without gear clash. The diagnosis attacked the cause rather than the symptom. Grinding did not happen because the lever lacked strength or because the driver had failed to push decisively enough. It occurred when components approached engagement while rotating at incompatible rates. Correct that difference first, and the final mechanical connection could become much less violent. Thompson's early system did not instantly become an industry standard. Automobile manufacturers had enormous investments in existing transmission designs, tooling, suppliers, and service practices. Any replacement had to survive far more than a successful demonstration. It needed to fit within a production car, operate reliably thousands of times, tolerate imperfect maintenance, and cost little enough to justify the benefit. Mechanisms that looked ingenious on paper could become impractical when manufacturing tolerances, lubrication, wear, and assembly were considered. Thompson continued refining his ideas and sought support from established manufacturers. The route from patent to production was therefore gradual. What interested Cadillac engineers most was not necessarily every automatic feature envisioned in the original mechanism. The speed coordinating principle itself offered a way to address one of the most persistent complaints of conventional manual shifting. Cadillac was a natural setting for the experiment. By the 1920s, the company occupied the luxury end of the American market, where refinement was part of the product. Buyers could receive a powerful engine, a carefully finished body, and a quieter, more comfortable cabin. Yet one poorly judged shift could still fill that cabin with the unmistakable sound of clashing metal. An experienced chauffeur could hide the harshness, but Cadillac had strong commercial reasons to make smoothness a property of the car, rather than a performance supplied by its operator. Development through the decade gradually produced a system suitable for regular manufacture. By the end of the 1920s, Cadillac and LaSalle automobiles were receiving what General Motors called Synchromesh. The crucial change happened before final engagement. Rather than allowing positive locking elements to meet while turning at substantially different speeds, the mechanism first used friction to reduce the mismatch. The principle can be understood without following every shaft inside the gearbox. Consider two rotating members that eventually have to lock together. One is turning faster. If the engagement teeth are forced together immediately, the difference appears as impact chatter or refusal to mesh. A synchronizing mechanism introduces friction surfaces first. Contact between them applies torque from the faster member to the slower one, reducing the difference between their speeds. Once the two are close enough, the locking elements can engage without the violent clash that previously punished a mistimed shift. Cone-shaped surfaces were particularly effective because their geometry could create useful synchronizing force within a compact space. The brilliance of the arrangement lay partly in what it refused to do. It did not solve gear clash by forcing the teeth together more aggressively. It created a brief controlled delay in which friction prepared the parts for engagement. The driver still operated the clutch and chose the ratio. The transmission had not become automatic, but an important intermediate action now occurred inside the gearbox rather than through an elaborate sequence at the pedals. Cadillac could therefore sell not just a new piece of hardware, but a different driving experience. A normal road shift no longer demanded the same precision in throttle timing that had distinguished experienced motorists from beginners. The benefit was immediately perceptible, even though the working parts remained hidden. A cleaner shift interrupted acceleration less. The driver spent less time pausing in neutral or listening for the exact engine note that signaled another attempt. The expensive automobile felt more consistent with the refinement promised elsewhere in its design. This was the central reversal in the story. For decades, road cars had required the operator to compensate for a gap in the transmission's behavior. Synchromesh began placing a physical mechanism in that gap. Yet the breakthrough should not be mistaken for a sudden arrival of the fully synchronized manual gearbox familiar later in the century. Cadillac's own operating instructions from 1930 make that clear. Synchronization covered changes involving intermediate and high gear. Low and reverse did not receive the same mechanism because Cadillac generally expected those selections to be made when the car was stopped or moving very slowly. If the transmission was still spinning, when the driver attempted to move from neutral into low or reverse, the instructions advised pausing after depressing the clutch, so the rotating parts could lose speed. The manual also discouraged shifting from intermediate into low unless the car was nearly or completely stopped. That detail is historically useful because it shows how practical innovations often enter production. Engineers did not necessarily apply a new mechanism everywhere simply because it existed. They placed it first where customers would gain the clearest benefit. Intermediate and high gears handled the road shifts drivers performed repeatedly while the car was moving. Low served mainly for starting and very slow operation. Reverse was normally selected at rest. Synchronizing every ratio would have added cost and complexity for situations that occurred less frequently. The result was not a failure to finish the job. It was a deliberate compromise. A driver of an early Synchromesh Cadillac could therefore experience old and new transmission behavior in the same car. Ordinary shifts through the commonly used ratios became easier, while low and reverse still rewarded patience. This selective implementation also warns against treating Synchromesh as one unchanging technology. Later passenger cars often synchronized all forward ratios, and some eventually synchronized reverse. Earlier examples varied. First gear remained unsynchronized in many manual transmissions, long after second, third, and top gear had received synchronizers. Drivers simply learned not to select first while moving quickly, or they used older speed matching methods when circumstances required it. The architecture around the synchronizer evolved as well. Sliding mesh gearboxes had physically moved large gears into engagement. Constant mesh designs allowed gear pairs to remain engaged continuously, while separate dog clutches or sliding sleeves determined which gear was locked to a shaft and therefore transmitted power. This reduced the need to slide the main gear teeth into mesh during every shift. But it did not remove the problem of differing rotational speeds. A dog clutch asked two sets of locking teeth to engage, and those teeth could still clash if the gear and shaft were not moving compatibly. Synchronizers fit naturally into this arrangement. They prepared the selected gear and shaft before the sleeve completed the lock. As constant mesh designs matured, the familiar sequence of later manual transmissions began to emerge. The gears could remain in mesh, quietly rotating until the driver selected one, while a synchronizer controlled the transition into engagement. Other changes contributed to refinement. Passenger car transmissions increasingly adopted helical gears because angled teeth enter contact more gradually than straight-cut teeth, reducing characteristic gear whine. Helical gearing brought axial forces that designers had to manage through bearings and case structure, but the improvement in noise and smoothness suited the expectations of road cars. Synchronizers did not cause the adoption of helical gears, and helical teeth did not solve synchronization. The two developments addressed different forms of harshness. Better bearings, lubricants, machining accuracy, and stronger cases worked alongside them. The gearbox was becoming quieter for several reasons at once. Once speed matching had become an internal function, engineers could refine the way it happened. Later, synchronizer designs used different friction cones, blocking arrangements, bulk rings, materials, and tooth forms. One important improvement was preventing the driver from completing engagement before synchronization had progressed far enough. A forceful movement of the lever could otherwise overwhelm the process it was meant to assist. Blocking ring designs addressed this by using friction and geometry together. Initial contact between cone surfaces began correcting the speed difference, while the ring temporarily resisted the sleeve's final movement. As synchronization approached, alignment changed and engagement became possible. From the driver's seat, the delay might amount to little more than a slight resistance felt through the lever. Inside the gearbox, several mechanical events had occurred in sequence. Such refinements mattered because road cars were becoming faster, heavier, and more numerous. A synchronizer had to absorb energy repeatedly without wearing out quickly. Its friction surfaces needed enough grip to perform their work, while the surrounding transmission still required lubrication strong enough to protect gears and bearings. Too little friction slowed or prevented synchronization. Too much could produce harshness or excessive wear. Lubricant chemistry, cone angle, surface area, rotational mass, and shift speed all influenced the result. These were no longer problems that could be solved by telling the driver to become more skilled. They belonged to transmission engineering. The consequences reached beyond luxury cars. As automobiles moved deeper into ordinary family and business life, manufacturers had reasons to reduce the procedural burden of driving. A customer did not need to understand cone friction or shaft speeds to appreciate a gearbox that accepted shifts without protest. Driving instruction became less tied to elaborate mechanical rituals. A newcomer could concentrate more on clutch coordination, road position, traffic, and selecting an appropriate ratio rather than memorizing how long a particular transmission needed to sit in neutral. That change did not make good technique irrelevant. Releasing the clutch carelessly could still shock the driveline, and matching engine speed during a downshift could improve smoothness. The difference lay in necessity. Double clutching remained valuable knowledge in some vehicles, but ordinary passenger car operation increasingly ceased to depend on it. Unsynchronized transmissions did not disappear. Heavy trucks continued using them because commercial vehicles faced different engineering priorities. Larger gears and heavier rotating components placed greater demands on synchronizers. A mechanism robust enough to handle those loads could add weight, cost, or shift time. Professional drivers could often achieve fast, reliable changes by matching speeds themselves, making a simpler, non-synchronized transmission attractive in applications where durability mattered more than ease for an inexperienced operator. Racing machinery followed its own priorities. Some competition gearboxes favored dog engagement designed for speed rather than the quiet smoothness expected in passenger cars. Motorcycles developed separate approaches. Older automobiles remained in service for decades. The survival of these designs did not contradict the value of Synchromesh. It showed that transmission engineering was never a contest toward one universal solution. Different vehicles placed different values on strength, cost, shift speed, longevity, noise, and required operator skill. For passenger cars, however, the direction was unmistakable. More forward ratios became synchronized, and gear changing became an increasingly ordinary action. The disappearance of gear clash from normal operation changed how motorists interpreted it. In an early car, grinding could be an expected consequence of imperfect technique. In a later synchronized transmission, the same sound increasingly suggested a worn synchronizer, a clutch that was not releasing properly, or a driver forcing a shift the mechanism had not completed. A once normal operating challenge had become evidence that something was wrong. That shift in expectation reveals how thoroughly synchronization had entered the automobile. When a synchronizer begins to wear, the older mechanical relationship can briefly return to the surface. A particular gear may resist engagement or grind, even though the lever is moved correctly. A driver who uses manual rev matching or double clutching can sometimes reduce the symptom, because those techniques help narrow the speed difference before the worn synchronizer has to do its work. What had once been standard practice becomes a workaround for failing hardware. The contrast would have been immediately understandable to a motorist from the crash box era. Earl Thompson continued working on transmission development as the industry moved beyond synchronized manual gearboxes. His career intersected with General Motors' larger efforts to automate shifting, eventually leading towards systems such as Hydra-Matic, introduced for the 1940 model year by Oldsmobile. Hydra-Matic was not simply a Synchromesh gearbox with extra parts, nor was it the achievement of one engineer. It emerged from broader work by GM teams on hydraulic control, planetary gearing, clutches, and automatic ratio selection. Its relevance here lies in the direction of travel. Synchromesh had shown that a difficult portion of shifting did not have to remain a conscious human task. Automatic transmissions extended that principle by taking over additional decisions and actions. The contrast is clearest when viewed across several generations of vehicles. A crashbox driver selected the ratio and managed the conditions needed for engagement. A synchronized manual driver continued choosing the ratio but relied on internal mechanisms for much of the preparation. An automatic transmission could also decide when the ratio should change and carry out the process with little or no direct intervention. Each stage redrew the boundary between operator and mechanism. Yet Synchromesh should not be treated merely as a temporary stepping stone toward automation. For millions of manual transmission cars, it became a durable solution in its own right. Drivers retained control over gear choice while receiving a far more forgiving interface with the rotating machinery beneath them. This combination mattered to enthusiasts, ordinary commuters, commercial users of lighter vehicles, and manufacturers selling in markets where manual gearboxes remained dominant. Synchronizer design therefore continued improving even after automatic transmissions became common. Materials became more durable. Multi-cone arrangements increased friction area for transmissions with larger speed differences or greater rotating mass. Shift mechanisms gained precision. Gear oils were formulated with synchronizer behavior in mind. Performance cars placed new demands on the system as drivers expected rapid changes at high engine speeds. The basic idea survived because it solved a problem elegantly. Use controlled friction to prepare components before asking them to lock. Looking back to Panhard and Levassor makes the scale of the transformation clearer. Their early gearbox architecture was genuine progress, not a primitive mistake awaiting correction. Multiple ratios allowed engines with narrow useful speed ranges to propel automobiles through conditions no single fixed drive ratio could handle well. Sliding gears were an understandable solution using the manufacturing methods and mechanical knowledge available at the time. The difficulty of shifting them emerged from the success of the automobile itself. Cars grew faster, journeys became longer, buyers expected refinement, and operating procedures that had once seemed acceptable began to feel burdensome. Engineering progress often works this way. A solution creates new expectations, and those expectations expose the next weakness. The synchronizer did not make multiple gears obsolete or eliminate the clutch. It changed one critical interaction within the existing system. The result was disproportionately important because it affected something a driver repeated dozens or hundreds of times during a journey. A single clean shift might seem trivial. Repeating that simplicity every day changed the character of the automobile. It also changed who could feel comfortable driving one. Mechanical familiarity remained useful, but it no longer had to be a prerequisite for moving through the gearbox without audible mistakes. Manufacturers could sell cars to people who wanted transportation rather than a continuing education in machinery. That broadening of usability was part of the automobile's transition into mass ownership. The same movement appeared elsewhere as manufacturers absorbed tasks previously performed by drivers, starting, ignition adjustment, lubrication routines, braking assistance, and eventually many aspects of steering and engine management. Synchromesh belonged within that trend, though its contribution remained unusually subtle because the mechanism operated only for a moment during each shift. It rarely became the feature people admired visually. There was no dramatic exterior shape announcing that rotational speeds had been equalized inside the transmission. Its success was measured by what did not happen. The lever did not bounce away. Teeth did not chatter. The driver did not need another attempt. As years passed, those absences became normal. By the middle decades of the 20th century, synchronized passenger car transmissions were familiar enough that drivers increasingly expected smooth engagement without deliberate double declutching. Many manuals still demanded thoughtful clutch use, and first or reverse gear could retain special procedures on some cars. But the old requirement to master every ratio through speed matching technique was fading. This altered driving instruction as much as machinery. A learner could be taught the pattern of the lever, the relationship between clutch and throttle, and when to choose another ratio without first becoming an apprentice gearbox operator. The transmission had become more forgiving without becoming mechanically simpler. In fact, greater simplicity for the driver depended on additional sophistication inside the case. Friction cones, sleeves, springs, rings, carefully shaped teeth, controlled clearances, lubrication, and manufacturing precision all worked together so that one movement of the hand could replace what had once been several carefully timed actions. That inversion is characteristic of mature engineering. Ease of use often appears only after complexity has moved away from the user. The early motorist confronted the machine directly. Every weakness in design presented itself as another procedure to learn. Later automobiles increasingly hid those negotiations behind mechanisms engineered to tolerate variation in human behavior. Synchromesh is one of the clearest examples because the old technique remained visible long enough to show exactly what had been removed from ordinary operation. A driver of an unsynchronized car had to listen for the engine, estimate road speed, pause in neutral, alter revolutions, and judge the moment when another ratio would accept engagement. A later driver could perform the same journey without consciously thinking about any of those internal speeds. The vehicle had not escaped the need for coordination. Engineers had simply embedded a controlled way of achieving it inside the transmission. This is why Thompson's historical importance should be described carefully. His patent work identified synchronization as a direct answer to gear clash, and his ideas became important in Cadillac's development of practical synchromesh. But mature manual transmissions were not created by a single patent or frozen in the form of one mechanism. Cadillac engineers adapted the concept for production. Other manufacturers developed alternative arrangements. Blocking systems improved. Friction materials changed. Lubricants, bearings, gears, and manufacturing tolerances advanced. Some designs synchronized more ratios than others, and different applications reached different conclusions about how much complexity was worthwhile. The larger achievement was cumulative. Once synchronization became an explicit function of gearbox design, engineers had a problem they could measure, refine, and optimize, instead of leaving it primarily to driver technique. That shift turned an old operating skill into a mechanical design discipline. It also explains why the synchronizer eventually became almost invisible in discussions of ordinary driving. Drivers usually notice a clutch pedal, the position of the gear lever, and perhaps the number of available ratios. Few think about the friction surfaces working for a fraction of a second beneath the floor. When everything is healthy, there is little reason to. The lever moves, the ratio changes, and the car continues. That apparent simplicity stands in sharp contrast to the opening image of an early driver hearing a gearbox reject a badly timed attempt. The sound, the resistance, the pause in neutral, and the adjustment of throttle were once part of learning how to make the machine cooperate. By the time Synchromesh became routine, those details had retreated into the mechanism. The historical transformation did not occur because gears became easier to mesh by nature or because rotational speed ceased to matter. It occurred because designers found a reliable way to manage the mismatch before final engagement. The driver still chose where the transmission should go. The crucial difference was that the gearbox finally learned to do that work for the driver.